Okay, so we plotted our graph and it's now time to analyse the graph and form a conclusion. So the next section we would write down is analysis and conclusion. And I like to start this section by just giving the briefest recap of your hypothesis. So I write in the hypothesis, it was expected that the square of the time period of the whirling bung would be directly proportional to the radius of the orbit. So just reminding the reader what your hypothesis was. It was expected that the graph would look like this. And let's just pop that graph in again. I put that in at the hypothesis. You may have a graph that you expected it to look like as well. So that just gives a little bit of context to the conclusion itself before we start. Now, for the conclusion, there are a series of questions that I would like you to ask yourself, and I'm going to pop them underneath here on the screen in a second, so you can ask yourself these questions about your data. If you ask yourself these questions and you answer these questions, your conclusion will be full and complete. So the first question I'd like you to ask yourself is, well, it's not a question. The first thing you do is you describe the pattern or the trend shown on the graph. So I certainly have a positive linear relationship here on this graph. The pattern shown on the graph is not graph, I won't write graph is a positive linear trend. Okay, first thing, can we write anything more about it? The line of best fit does not go through the origin. However, the maximum and minimum lines of best fit span the origin. It is therefore reasonable to conclude that the square of the time period of the whirling bung is directly proportional to the radius of orbit. So we described the pattern or the trend that you can see on your graph at the moment and brought it back to your hypothesis. So we can say, yes, I think it's reasonable to conclude that these two variables are directly proportional. Now what I'd like to do is take the values of gradient and come up with an uncertainty in the gradient, which will give me an idea of how precise the results are. So let's write down what the gradients are. So the best fit gradient is equal to 1.449. Can't just give a number, we have to give units, and that will be s squared divided by m, so m to the minus 1, okay? So s squared, m to the minus 1, because we've got time squared divided by meters, so that will be the units of the gradient. The minimum line, the minimum fit line, the gradient value is 1.26. I'll just copy the units from there. And the maximum fit line is equal to 1.6. And we'll give it to 2 decimal places. In fact, I think we'll give the best fit line to 2 decimal places as well to make it consistent. And the units are the same as before. So we have the three values of gradient. Our best fit line we'll stick with, so the gradient is actually equal to 1.45. And this value here, plus or minus, what we do is we take half of the range from the two values. So 1.6 minus 1.26 divided by 2, so half the range. So that's going to give us plus or minus 0.17, and the units are the same as before. What we have here is we have an idea of what the gradient is, but also an idea of how precise that gradient is, an idea of uncertainty on it. It doesn't tell us much, so what I'd like to do is calculate the percentage uncertainty. So that's going to be 0.17 divided by 1.45, and then multiply the whole thing by 100%. Will give us 12%. So the percentage uncertainty in the value of gradient is 12%. That tells us that the results are not very precise and they're not very reliable. Okay? That means, I think anything under 10% would say that it's precise, but anything over 10% says we're not too precise. Okay? So the uncertainty, let's comment on that, in the gradient is 12%. Let's say the percentage uncertainty, which suggests that the precision of results could be improved. At this stage, we've commented on the pattern shown. We've found the percentage uncertainty in the gradient. We could also comment on the reliability. To comment on the reliability, you analyse the spread of points around the line of best fit. Now, those points around the best fit look pretty good to me. The error bars are slightly big at the larger end of the scale, but they generally do fit on all of the lines apart from this point at 0.8. So the results can be considered to be fairly reliable given that the points all lie closely to the line of best fit. There is a slight anomaly for the data point r equals meters, where it sits just below the trend shown by the other points. However, when the error bars are taken into account, the best and minimum fit line pass through this data point. So we've said, yeah, the results are fairly reliable because the points all lie closely to the line of best fit. Obviously, if your points lie far away from the line of best fit, your results are not reliable. At this stage, you might be able to take your gradient and calculate something. So you might be able to calculate gravity. You might be able to calculate the mass of something. And I could do that with mine. I could take my gradient and come up with a value for gravity there, and I could compare it to the actual value of gravity. I'm not going to do that just now, because that was not the aim of my investigation. The aim of my investigation was to, we remind ourselves, how does the radius of a whirling bung affect the time period of one orbit of the bung? Okay, so we've taken the graph, we've said what our hypothesis would be, we've commented on the trend, we've given an uncertainty in the gradient, we've talked about how that's the precision of the results, and we've talked about how reliable the results are. If this line had consistently gone through the x-axis when it should have gone through 0, or if it had consistently intercepted on the y-axis when it should have gone through 0, we could have considered some form of systematic error. But in this case, I'm not sure it really applies. So I think my conclusion is generally finished. I'm going to finish it off with one whole sentence. I'm going to say, in conclusion, the radius of the whirling bung orbit is directly proportional to the square of the time period of one complete orbit. Job done.